This is the video on mechanical energy. So I've already asked this question, well, what can energy do that momentum cannot? That brings us to the law of conservation of energy. Basically, it states energy cannot be created or destroyed. It can only be transferred from one place to another, and it can also transform or change into another form of energy. So what is mechanical energy? Right. So we learned about mechanical energy before a little bit. We learned about what it is, and it is the kinetic energy, gravitational potential energy, and elastic potential energy. Now, mechanical energy is the energy due to the position of something or the movement of something. There are three different forms of mechanical energy. Well, you have the movement of something, which is kinetic energy. And you have potential energy. There are two types of mechanical potential energy: of gravitational potential energy and elastic potential energy. Potential energy is the stored capacity to do work due to its location in a force field. So like I said, we have gravitational potential energy that's represented by mass times gravity times height. Elastic potential energy is 1/2 times the spring's constant times the distance that, or the displacement that it is stretched or compressed. And you do have kinetic energy, 1/2 times mass times velocity squared. So mechanical energy, it can be transformed into other forms of mechanical energy. So you can see that, like, in an isolated system, if there are no losses to friction, then we say that the total mechanical energy of the system is conserved. So basically what you're saying is you're adding these together. Your mechanical energy is your kinetic energy, your gravitational potential energy, and your elastic potential energy added. The total amount of mechanical energy will not change, right? The number does not change, but the different forms of the mechanical energy will change, but they have to add up to that same amount, assuming no loss, right? So the total amount of mechanical energy, you just add up those three kinds. We're not including the chemical potential energy. We're not including internal energy, rest mass, energy loss to heat, sound, light, etc. We'll get to that later, right? So in order to reinforce this, we did the popper lab, right? In which you have this toy, the popper, where you bend it back, you set it on the table, and let it pop, right? So we asked those kinds of questions, like, right? So we needed to find out how high it went, calculate the gravitational potential energy. Then we needed to talk about the different types of energy it had at different points, right? So what type does it have when it reaches the maximum height? What type of energy does it have, or calculating the elastic potential energy? What type of energy does it have the instant it pops? What type of energy does it have as it's moving up towards the peak? And what type of energy does it have at the peak, right? So these are the different uh, questions that can be asked. And as well, like, when is the popper moving the fastest, right? So essentially what's happening is all of that mechanical energy is elastic potential energy when it's pulled back, sitting on the table. The instant it pops, all that energy is transformed into kinetic energy. Now, as that popper is moving up to the peak, that kinetic energy is transforming into gravitational potential energy, and at the peak, it's all gravitational potential energy. But at any point, if I added up all three of those energies, it's going to have to equal my total amount of mechanical energy. The total amount doesn't change, but just the different forms that you have does change, right? Because all that energy is transforming. What happens to an object's kinetic energy and gravitational potential energy as it falls? So in order to answer this, we did this energy skate park, and it is this simulation here, right? So we did have this bank of pie charts, and this is what happens, right? So the blue is the gravitational potential energy. The green is that kinetic energy. So if we look at this, let's look at point A and point F, right? So you'll notice that those are the same. Same thing with points B and point C. Those are the same, right? So the total amount does not change, but you notice at the same height, those forms of energy are the same. So the mechanical energy, as this skater is going up and down the ramp, it's transforming gravitational potential to kinetic, kinetic to gravitational potential energy. The skater is going to be moving the fastest at the bottom, and you'll notice that pie chart is all green. It's moving the fastest because that is where all of that mechanical energy is kinetic energy. That's the lowest point, right? So all of that gravitational potential energy has been transformed into kinetic energy. How can mechanical energy be used to gain an advantage in the carnival game Roller Bowler? That brings us to Over the Hill. Right, so you look at this, and we have the straightaway, which is that point A, the hill, which is B, C is the valley, D is going to be the ramp at the very end. So what form of mechanical energy does it have at different points? We're assuming A and C are at the ground, they're at the same height. So it's going to have kinetic energy as it's rolling along point A. As it goes up point B, some of that mechanical energy is transformed into kinetic energy. So I have gravitational and kinetic energy as it moves over the hill. It goes back down into the valley. It's transformed back into kinetic energy. And as it goes up to point D, it should come to rest at some point along that ramp where it's all gravitational potential energy. Right, so those are the different forms of energy as it goes over there. What must be true of the conditions of the points, right? So what I want you to get out of this is that point D, that ramp has to be taller than point B. And that's because you're going to have a little bit of kinetic energy moving over that hill, right, down. Now, as it goes up the ramp on the other end, it's going to, you're going to need to convert all that mechanical energy into gravitational potential energy once it gets up to the peak. And if the ramp, that point D, is lower than point B, it won't be able to do that. It'll have some mechanical energy left over as kinetic energy, and it'll move off the ramp. So assuming no loss to friction, point A and point C are at the same height, they're going to have the same velocity. They have the same gravitational potential energy, they have the same kinetic energy, right? So they're going to have the same velocity. So the next two questions ask about maximum and minimum velocities, right? So essentially, this is how you do that. Let's just assume at the top of point B, on top of the hill, it takes 10 joules of gravitational potential energy just for that marble to be on top. Well, you're going to have to give it enough kinetic energy, a little bit more than 10 joules, so you're going to have a little bit of kinetic energy left over. If not, if you don't give it 10 joules of kinetic energy on the straightaway at point A, it won't make it over. It's not going to have enough energy to convert it into gravitational, have a little bit of kinetic left over. Same thing with the maximum point. Let's just say I put that marble on top of point D and it has 12 joules of gravitational potential energy. Well, once it moves over the hill, you're going to 12 joules. You're going to need to give it at least that much kinetic energy at point A. Otherwise, it's not going to have. Otherwise, it's going to move off the ramp. So that's how you find that window, and then you use that equation for kinetic energy, which is found down there, in order to work backwards to find that velocity. Right. So that's how it is. Right. And the last one is, would it even be possible to push the marble on the straightaway, have it come to rest in the valley without some mechanical energy being lost to internal energy? Answer is no. And that's because if I didn't lose any energy, you're going to have a little bit of kinetic energy going over that hill at point B. Well, coming back, you're still going to have that just little amount. You need to have as little amount of kinetic energy as possible going over point B, and then you're going to need to lose that amount of mechanical energy to the outside world due to heat, sound, like friction. So when it comes back, it does not have enough mechanical energy to go back over the hill. So let's just take a look at this, right? So here's a good concept here. We'll just look at the energy. At what points along this track is the marble going the fastest, right? How do you know this, right? So it's going to be point C and E because they're at the lowest, right? That mechanical energy has the least amount of gravitational potential energy, and it's transformed into kinetic energy. At what point along the track is the marble going the slowest? I'm going to look at this, and I'm going to say it's going to be point A. It's at the highest point. Most amount of gravitational potential energy, least amount of kinetic energy. What 2 points on the track is the marble going the same speed? C and E, they're at the same height. Rank the points along the track, you will be going from fastest to slowest, right? How did you come to this answer? Real easy. All you do, if I'm asking you fastest to slowest, you just start from the bottom, work your way up. So go C, E, right? They're the same. D, B, A. Right. If I ask slowest to fastest, you just go from the top down. A, B, D, C, and E are the same. Right? So without any external forces, will the marble ever be able to go higher than point A? Why or why not? The answer is no, and that's because if it starts at rest at point A, that's where all that mechanical energy is, right? You would need more mechanical energy to be at a higher point than that, and you just don't have that. All right, so let's take a look at a pendulum, right? At what point along the path is the pendulum going the fastest? It's going to be point B. that's the point where it's at the lowest. Least amount of gravitational potential energy, most amount of kinetic energy. What point along the path is the pendulum going the slowest? It's going to be point D, because it's at the highest point. Most amount of gravitational potential energy, least amount of kinetic energy. In fact, at that point, it's at rest. Rank the points on the pendulum with the letters fastest to slowest. How did you come to this? So once again, you're just going to start from the bottom, work your way up. B, C, A, D. Right? If I ask slowest to fastest, D, A, C, B, just because you work your top down. Right? Real easy. Without any external forces, will the pendulum ever go higher than point D? Why or why not? Answer is no. Cannot create or destroy energy. If all the mechanical energy is gravitational potential energy, it would need more mechanical energy to be at a higher point, right? All right. So, do you trust the laws of physics? This is the bowling ball demo that you've probably seen like videos of. What type of energy do the balls have the instant lets it go? All gravitational potential energy. As it's moving down, as it's swinging down, the gravitational potential energy is transforming into kinetic energy. At the very bottom, that's where it's going to have the most amount of kinetic energy. Now, as it's swinging back up, that kinetic energy is being transformed back into gravitational potential energy. Now, when it comes to rest, all gravitational potential energy. Now, if he releases it, like you can see from the nose, will it ever come back and hit him in the face? The answer is no, right? Because the highest point it could possibly be even without any losses due to friction or like air resistance, the highest point it can get is that initial point. So if it starts on your nose, it's going to come back and just tap them on the nose again. But we are losing some energy to the outside world, so it's not going to come back to that initial height. So yeah, it'll never come back and hit him in the face because energy cannot be created or destroyed. At the peak of the swing, all that energy is gravitational potential energy. It'll transform to kinetic energy, vice versa, but the total amount, mechanical energy, will never increase. Some of that energy will be changed due to internal energy lost to air resistance as well. So once again, there is just too much unknown in the universe to take a break from learning. Get out there and question everything.